Hi everyone, this is Abhinav. So we have been doing a series of virtual memory related videos based on the article that I wrote on the same topic a few weeks back. So many of you have really enjoyed this format of the article, and I think the topic is also something you know many people want to understand well. So I also want to make these videos covering the same set of topics, but in a more conversational or direct manner. So in the last video, we talked about what is virtual memory and why does it exist. And in this video, we are going to talk about the size of virtual address space of the process. So before starting this video, let's quickly recap what we talked about in the last video. So we learned that uh, virtual memory exists as a mechanism for the operating system to safely share physical memory amongst multiple processes that are running concurrently on the same system. Because because if one process is using a certain address, then that address should not be read or written by another process, and that can only be possible if the operating system is between sitting between uh, between the process and the memory itself, and that is done by the virtual memory layer. So operating system gives every process its own virtual memory, its own private address space, and that is a virtual address space, so it's not really real, and the process will treat it as real memory. It will read virtual addresses, write virtual addresses, and those reads and writes are handled by the hardware. So the hardware has memory management unit which translates those virtual addresses into physical addresses and then does the actual memory access. And it does those translations with the help of the operating system. So because operating system does this mapping of virtual addresses to physical addresses, and it maintains those mappings somewhere in the kernel, and the memory management hardware MMU will look up those mappings and figure out what is the mapping, you know, where does this memory access go in physical memory, and does this goes there and reads or writes on the data. So that's what we learned in the last video. Now in the topic of this video is size of virtual memory. So every process receives its own private virtual memory, and as a result it has this virtual address space. So what is the size of that space? So this space consists of addresses, and basically the question is how many addresses it can have, or how much memory can those addresses access. So let's do that again by discussing this from the first principles. Uh, so with any address, how much memory you can access, the question goes to the size of the address. So for example, if our virtual address is just 1 bit, then there are two possibilities. You can access either byte 0 or byte 1, which means you can access up to 2 bytes of data, or the size of the virtual address space is 2 bytes if your virtual address is 1 bit long. If your virtual address is 2 bits wide, then there are four possible values: 00, uh, 01, 10, and 11, which means 4 bytes. So your virtual address space becomes 4 bytes wide. Now, in a general case, if your virtual address is n bits, so you can get the idea. Uh, your physical address, or the virtual address space, will be 2 to the power n bits, n bytes. So that is the general formula. So if your virtual address is n bits wide, then your virtual address space will be 2 to the power n bytes. Um, so now let's talk about more, real hardware. So more hardwares come in all forms and sizes, but I'll stick to 64 bits in all of these videos, and even in my article I've stuck to 64 bits. So modern day servers, laptops, desktops are mostly 64 bits. uh, so which means, so what does that mean? So one of the things, or one of the implications of having a 64-bit processor is that the register size is also 64-bit wide. Um, so you have registers which are 64-bit. So, and what this means is that your virtual address space, what your virtual address also has to fit within a register, because uh, if uh, if the compiler is generating an instruction to read a particular byte in memory, so it will have to generate an instruction where the address goes into the register, uh, and then the read instruction has to be emitted. So basically, the processor has will go and read the address from the register itself. So if the address doesn't fit in a register, then it's a problem. So which is why the maximum size of a virtual address on 64-bit hardware can be 64 bits. So that is the maximum. But so which means that uh, if your virtual address is 64 bits, then your virtual address space becomes 2 to the power 64 bytes, which means that you can theoretically map up to 2 to the power 64 bytes of physical memory as well. If your virtual address is this much, then you can map the same amount of physical memory as well. But this is an extremely large amount of RAM, and we don't really have computers right now, or it may not be possible for a very long time to have computers with this much amount of physical memory. So the hardware designers uh, were conservative, because the more there are implications on the performance of the software as well. So if you create a extremely large virtual address space, the translation costs also increase. So the hardware designers came up with a more conservative size. So they said, for you know until we are for a until we have computers which can actually have 60 RAM, 2 to the power 64 bit bytes of physical RAM. They said that 48 uh, bits of a virtual address can be 48 bits wide. uh, 48 bits, which means that you can access the size of virtual addresses space becomes 2 to the power 48 bytes. And 2 to the power 48 bytes is 256 terabytes. So in present day hardware, usually you have virtual addresses that are 48 bits wide, and that results in a virtual address space of 256 terabytes. Theoretically, you can map uh, 256 terabytes of physical memory with this with a 48 bits wide virtual address. Uh, there are also some uh, l- you know some Linux kernels recently where you have 57 bits uh, wide virtual address. Uh, so that has an implication on how the mapping is done. But yes, so the more common variation is virtual addresses that are 48 bits wide, but we also have Linux kernel which has 57 bits uh, wide virtual address. So the difference is that with 48-bit wide virtual address, you need, if you're familiar with page tables that we will cover in the future videos, so you need 4 levels of page tables. With 57 bits virtual address, you need 5 levels of page table. So this basically allows, as you can guess, 57 bits wide virtual address means you can access or you can address much more amount of physical memory with it. Whereas with 48 bits wide virtual address, you can access up to 256 terabytes. So in this whole video series, and even in my article, I have stuck to 4 level of page tables and 48-bit wide virtual address plus. But you have to remember that we also have 5 level page tables and 47 bits wide virtual address. Um, so that is the size of the virtual address space. So every process that is created receives this much amount of virtual address space. So it is possible to map that much amount of physical memory. Now you must be wondering, we don't even today we don't have hardware which has 256 terabytes of physical memory. So how does it really work? So, for example, your laptop may have 16 GB of RAM, and your process has 256 terabytes of virtual address space. So, how does that really work? Is it possible that you can access any address in this range and it will work? And not really. Uh, so this is possible, like this difference between virtual address space and physical address space is possible because this mapping of virtual to physical memory is done by the kernel, and the kernel is aware of how much physical memory that is available. So it will make sure that any process cannot uh, grow beyond what is available. So it will not allow any mapping which is not really going to uh, make sense, or which is which cannot really exist depending on the size of actual physical memory available. um, but having a consistent uh, virtual address space makes things simpler, because the same operating system kernel compiled can run on on a variety of devices. So on a laptop with 16 GB of RAM, and on a server with 256 GB of RAM, the same kernel can be compiled and run. So they don't have to keep uh, you know different kind of code or handling in the code to handle different sizes of physical memory. So because the kernel basically abstracts away that the process of mapping. So that is the size of virtual memory address space, and how uh, you know uh, the operating system makes sure that uh, mappings are within the limits of the physical memory. Now, there is one more point here. Even though you have 256 terabytes of address space, virtual address space, not all of that is available to the process itself. So this is split into half. So um, so there is um, so it is split into half. So there's kernel address space, and then there is user space addresses. So on 64-bit systems, uh, it is split evenly. So you have 128 terabytes addressable in the user space and 128 terabytes